Welcome! In this session, we'll tackle problem number 1796, second largest digit in a string. This is a great problem to practice basic string manipulation and logical thinking. Let's dive in and explore how to solve it step by step. In this problem, you are given a string that can contain uppercase and lowercase letters, digits, and special characters. Your task is to identify the second largest numerical digit that appears in the string. A numerical digit refers to any character between 0 and 9, so we are only concerned with these. The second largest digit is defined as the second highest unique value among all the digits in the string. If the string contains fewer than two distinct numerical digits, you should return -1. For example, if the string has no digits at all or only one unique digit, the second largest digit does not exist, and the output must be -1. The output of the function is an integer that represents the second largest numerical digit in the string, or -1 if there aren't enough distinct digits. Let's look at some examples to clarify. In the first example, the input string is DFA12321AFD. Here, the distinct numerical digits present are 1, 2, and 3. Out of these, the largest digit is 3, and the second largest digit is 2. Therefore, the output for this input is 2. This demonstrates how we determine the second largest digit by first identifying all unique digits and then finding their relative order. In another example, the input string is ABC1111. This string only contains the digit 1, repeated multiple times. Since there is only one unique digit, there is no second largest digit. In such cases, the output should be -1. This highlights that the problem is not just about counting digits but specifically about identifying distinct values and considering their hierarchy. If fewer than two unique digits are present, the result is always -1. Now consider the input SJHTZ8344. The distinct numerical digits in this string are 3, 4, and 8. Among these, the largest digit is 8, and the second largest digit is 4. So, the output for this input is 4. This example demonstrates that even if some digits occur more frequently than others, we are only interested in their uniqueness and relative order. The constraints ensure that the input length will be between 1 and 500 characters, and you can expect a mix of letters, digits, and possibly special characters. Remember, edge cases like strings without digits, or strings with only one unique digit, must also return -1. Efficient handling of these scenarios is crucial to solving the problem correctly within the given constraints. To begin, let's explore a brute force approach to solve this problem. The intuition here is fairly straightforward. Since we're looking for the second largest digit in the string, we can start by iterating through all the characters to extract the digits. Once we have all the digits, we convert them to integers, remove duplicates, and sort them in descending order. After sorting, the second largest digit will be the second element in the sorted list. If no such value exists, for example, if there are fewer than two unique digits, we return -1 as specified in the problem. Now, in terms of efficiency, the time complexity of this approach includes O, n, for extracting digits and O, k log k, for sorting, where k is the number of unique digits, which is at most 10. The overall complexity is O, n plus k log k. For space, we require O, k, to store the unique digits. However, the drawback here is that sorting introduces unnecessary overhead. Since we only need the two largest digits, sorting the entire collection is inefficient and can be avoided, especially when dealing with larger inputs. Now, let's look at a more efficient alternative, the optimized linear approach. The key insight here is that we don't actually need to sort all the digits. Instead, we can dynamically track the two largest unique digits as we traverse the string. To do this, we initialize two variables, largest and second_largest, both set to -1 initially. As we go through the string, we check each character to see if it's a digit. If it is, we convert it to an integer and compare it with our current largest and second_largest values. If the digit is greater than largest, we update both variables, largest becomes the new digit, and second_largest takes the previous value of largest. If the digit is smaller than largest but larger than second_largest, we simply update second_largest. Once the traversal is complete, second_largest will hold the result. This approach is highly efficient, with a time complexity of O(n), since we only traverse the string once, and a space complexity of O(1), because we're not using any additional data structures. Additionally, this method handles edge cases, like strings with no digits or fewer than 2 unique digits, by returning -1 in those scenarios. The simplicity and efficiency of this approach make it a clear improvement over the brute force method. With these considerations in mind, we've chosen the optimized linear approach as our final strategy. This method stands out for its simplicity, efficiency, and minimal memory usage. By dynamically tracking the 2 largest digits as we traverse the string, we eliminate the need for sorting, which makes it particularly well suited for handling large inputs. Moreover, we avoid unnecessary computations while maintaining clarity in the implementation. When comparing the two approaches, the brute force method is easier to implement but less efficient due to the overhead of sorting. On the other hand, the optimized linear approach, while slightly more complex to code, achieves linear runtime and uses constant space, making it the superior choice for competitive programming scenarios. In conclusion, while the brute force approach is a viable option, the optimized strategy is more effective in terms of both time and space complexity, which is why it's the ideal solution for this problem. To solve this problem, we need to find the second largest digit in a string that contains both letters and numbers. The first step is to parse the input string to isolate the numeric digits. This means we traverse the string character by character, checking if each character is a digit. In Python, for example, we could use the isDigit method to do this. By filtering out only the numeric characters, we ensure that non-numeric characters don't interfere with our calculations. Next, we convert these digit characters into integers and store them in a set. Using a set is important because it automatically removes duplicates, which simplifies processing later. This step not only ensures that we are working with unique digits but also reduces the number of comparisons needed in subsequent steps, making the process more efficient. Once we have a set of unique numeric digits, the next step is to sort them in descending order. Sorting in descending order allows us to directly access the largest digit at index 0 and the second largest digit at index 1. To do this, we first convert the set into a list, as sets cannot be sorted directly. Then, we use a sorting function, like Python sort, reverse equals true, to arrange the digits in descending order. After sorting, we determine the second largest digit by checking if the sorted list has at least 2 distinct elements. If it does, the second largest digit is at index 1. However, if there are fewer than 2 distinct digits, we return -1, since a second largest digit does not exist in such cases. This step ensures our algorithm handles both typical and special cases correctly. This approach is built on a few key insights. First, by filtering out non-numeric characters early on, we ensure that the rest of the algorithm focuses only on relevant data. Second, using a set to store digits ensures that duplicates are eliminated efficiently, without requiring manual checks. Third, sorting the digits in descending order simplifies the process of identifying the largest and second largest elements. Finally, the algorithm is designed to handle edge cases, such as strings that contain no digits, strings with a single digit, or strings where all digits are duplicates. For example, if the input is ABC, there are no digits, so the result is -1. If the input is 111, there's no second largest digit, so we also return -1. But if the input is ABC 123, the second largest digit is 2, as the unique digits are extracted and sorted into 3, 2, 1. These insights ensure that the solution is robust and handles all possible scenarios. Analyzing the complexity of this algorithm, we see that extracting digits from the string has a time complexity of O(n), where n is the length of the string. Sorting the unique digits has a complexity of O(k log k), where k is the number of unique digits, which is at most 10 since digits range from 0 to 9. This makes the overall time complexity O(n), as the sorting step is dominated by the linear traversal of the string. For space complexity, we require O(k) to store the unique digits in a set. Regarding edge case handling, the algorithm is designed to return -1 in situations where no digits are found, only one unique digit exists, or all digits are duplicates. For example, if the input is A1B2C3, the extracted digits are 1, 2, 3, duplicates are removed to form 1, 2, 3, the digits are sorted into 3, 2, 1, and the second largest is returned as 2. This comprehensive analysis ensures the algorithm is both efficient and reliable for all input scenarios. This Python code solves the LeetCode problem number 1796, second largest digit in a string. The goal is to find the second largest digit in a given alphanumeric string. If no such digit exists, the function must return -1. The solution begins by defining a function's second highest within the solution class. The function takes a string s as input. To efficiently identify digits, it uses a set called unique_digits to store only unique numeric digits found in the string. Using a set ensures that duplicate digits are automatically ignored. Next, the function iterates through each character in the string s. For each character, it checks whether it is a digit using the isDigit method. If the condition is satisfied, the digit, converted to an integer, is added to the unique_digits set. Once all characters have been processed, the unique digits are converted into a sorted list in descending order. This is done using Python sorted function with the reverse equals true parameter. The digits are now arranged from the largest to the smallest. The function checks if there are at least 2 digits in the sorted list. If not, it returns -1 because there is no second largest digit. Otherwise, it returns the second largest element, which is at index 1 of the sorted list. This implementation is efficient due to the use of a set for uniqueness and the sorting process, which operates on only the numeric digits. The overall time complexity is O, n plus k log k, where n is the length of the string and k is the number of unique digits. The space complexity is O, k, due to the storage of unique digits in the set. This is the Java implementation for LeetCode problem number 1796, second largest digit in a string. The logic mirrors the Python solution by using a tree set to store unique digits in descending order. Java-specific features like tree set and character.isDigit are utilized to ensure correctness and simplicity. The code handles edge cases where there are fewer than 2 unique digits by returning -1. To solve this problem, we start by analyzing the input string, which in this case is DFA12321AFD. The first step is to create an empty set called unique_digits. This set will help us keep track of all the unique digits we encounter as we iterate through the string. Next, we loop through each character in the string one by one. If the character is not a digit, we simply skip it. For example, the first 3 characters, D, F, and A, are not digits, so we ignore them. When we reach the character 1, we see it's a digit, so we add it to unique_digits, making the set now contain 1. Similarly, we add 2 and 3 as they are digits, updating the set to 1, 2, 3. Any repeated digits, like the second 2 or 1, are skipped because they are already in the set. Lastly, the remaining non-digit characters are also ignored. By the end of this step, unique_digits contains all unique digits from the string 1, 2, 3. Now that we have all the unique digits in the set, the next step is to sort them in descending order. After sorting, we get the list 3, 2, 1. Once we have the sorted list, we check if it contains at least 2 elements. If it does, we can safely access the second largest digit, which is the second element in the sorted list. In this case, the list has 3 elements, so the second largest digit is 2. This is our result. For the output, we return 2. Moving on to the next example, consider the input string ABC1111. Just like before, we start by creating an empty set called unique_digits. When examining the string ABC1111, we iterate through each character. The first 3 characters, A, B, and C, are not digits, so we skip them. Upon encountering the character 1, we identify it as a digit and add it to unique_digits, making the set 1. The remaining characters in the string are all 1, but since 1 is already in the set, we skip them. At this point, the unique_digits set contains only 1 digit, 1. The next step is to convert this set into a sorted list in descending order, which results in 1. However, when we check the length of this list, we see it contains only 1 element. Since there isn't a second largest digit, we return -1 as the output. Now let's evaluate another input string, SJHTZ8344. We begin in the same way by creating an empty set called unique_digits. Looking at the string SJHTZ8344, we start iterating through each character. The first 5 characters, S, J, H, T, and Z, are not digits, so we skip them. When we reach the character 8, we recognize it as a digit and add it to unique underscore digits, making the set 8. Next, the character 3 is a digit, so we add it to the set, updating it to 8, 3. The character 4 is also a digit, so we add it to the set, resulting in 8, 3, 4. The last character, another 4, is already in the set, so we skip it. At this point, the unique underscore digits set contains all unique digits from the string 8, 3, 4. We then sort this set in descending order to get the list 8, 4, 3. Since the list has more than one element, we can access the second largest digit, which is 4. This becomes our result. Finally, for the input string sjhtz8344, the second largest digit is 4, which we return as the output. With this, we've completed the solution walkthrough for all 3 examples. By following these steps, extracting unique digits, sorting them, and identifying the second largest, we can efficiently solve the problem for any input string. The time complexity of the function's second highest is determined by analyzing each step in the process. First, we iterate through the string s character by character. If the length of the string is n, this loop runs n times, contributing an O(n) complexity. For each character, we check if it's a digit using the isDigit method. Since this check is a constant time operation, and it is performed n times, its total contribution is also O(n). Next, when we add a digit to the set unique underscore digits, the average time complexity of the add operation is constant, or O(1). Even if we add all digits from 0 to 9, the maximum number of possible unique digits is 10, so the contribution remains O(1). After that, we sort the unique digits using the sorted function. Sorting a set of at most 10 elements results in O(10 * log 10, which simplifies to O(1) due to the small, fixed size. Finally, accessing the second element in the sorted list is a direct indexing operation, which is also O(1). Combining these steps, the overall dominant term in the time complexity is the O(n) for iterating through the string. The total time complexity of the function is therefore O(n). While other operations like adding to the set, sorting, and accessing elements have constant time contributions, the linear traversal of the string dominates the complexity. Now, let's consider the space complexity. The primary contributor to space usage in this function is the set unique underscore digits, which is used to store unique digits from the string. Since the set can only hold a maximum of 10 unique digits, the space required is constant, or O(1). Similarly, the sorted list sorted underscore digits, which is generated from the set, also contains at most 10 elements. This requires O(1) space as well. Lastly, the space used by other variables, such as the input string s, the loop variable char, and any intermediate integers, is negligible in comparison and does not scale with the size of the input. Therefore, the overall space complexity is determined by the constant storage requirements of the set and sorted list. Combining these observations, the total space complexity of the function is O(1). This is because the space usage does not grow with the size of the input string, it remains constant regardless of how large the input is. To put this solution in perspective, let's compare it with a naive or brute force approach. In a naive approach, one might extract all digits from the string into a list, convert them to integers, and use nested loops to find the second largest digit. While this approach would still take O(n) to iterate through the string and extract digits, finding the second largest digit with nested loops would require O(n² time. Additionally, storing all digits in a list would result in a space complexity of O(n), which scales with the size of the string. In contrast, the optimized approach uses a set to store only unique digits and sorts at most 10 elements, reducing both the time complexity to O(n) and the space complexity to O(1). This makes the current solution significantly more efficient. In summary, the proposed solution is optimal for solving this problem, achieving linear time complexity and constant space complexity. By leveraging the properties of sets to handle unique digits and sorting only a small, fixed number of elements, the solution avoids the inefficiencies of a naive approach. This efficiency is particularly important for handling large input sizes, where the advantages of O(n) time and O(1) space become even more pronounced. The combination of simplicity and optimization makes this approach an excellent choice for the problem of finding the second largest digit in a string. When solving this problem, there are a few common mistakes to watch out for. First, not handling non-digit characters properly can create issues. If you assume the string contains only digits, symbols or letters in the input could cause runtime errors or lead to incorrect results. Always filter out anything that's not a digit. Another frequent mistake is failing to handle duplicate digits. For instance, if the string contains multiple occurrences of the same number, forgetting to remove duplicates might result in an incorrect value for the second largest digit. Additionally, overlooking edge cases can be problematic. If there are fewer than 2 unique digits, such as in an empty string or a string like 444, your solution needs to handle this gracefully. Finally, incorrect sorting logic is another pitfall. Sorting strings instead of integers may lead to lexicographical order, which doesn't work for numbers. For example, 10 would be considered smaller than 2, which is clearly wrong in this context. Now, another common issue is suboptimal complexity. Some solutions use nested loops or sort the entire array of digits when, in reality, you only need the 2 largest values. This can drastically increase time complexity, making the solution less efficient for larger inputs. Instead, a more optimal approach for this problem is to use a single pass through the string. By maintaining 2 variables to track the largest and second largest digits, you can achieve an O(n) time complexity. This problem is also a great example of a pattern you may encounter in interviews, finding the kth largest element. It's a classic topic, and recognizing this pattern can help you identify optimal solutions quickly. Be sure to consider edge cases, like strings with no digits or strings with only 1 unique digit. Lastly, avoid overcomplicating your solution. Sorting the digits, for instance, is unnecessary when only the top 2 are required. Simplicity often leads to better performance and fewer bugs. This problem shares similarities with others you might encounter during your coding practice. For example, LeetCode problem 414 involves finding the third maximum number, while problem 215 focuses on the kth largest element in an array. Problem 976 deals with constructing the largest perimeter triangle, and problem 692 asks for the top k most frequent words. Each of these problems requires careful handling of values and optimization strategies. Now, looking at alternative approaches, the brute force method involves extracting all digits, sorting them, and then finding the second largest. While this approach is straightforward, it has a time complexity of O(n) log n due to the sorting step, which can be inefficient for larger inputs. On the other hand, an optimized single-pass approach uses 2 variables to track the largest and second largest digits as you iterate through the string. This reduces the time complexity to O(n), making it much more efficient, though it requires extra attention to edge cases. Another alternative is the heap-based approach, which can be particularly useful in generalized kth largest scenarios. Here, you use a min-heap of size 2 to maintain the largest and second largest digits as you traverse the string. The time complexity for this method is O(n) log k, where k is 2 in this case. While this approach is technically valid, it tends to be overkill for this specific problem, where simpler solutions like the single-pass method are more efficient. However, understanding the heap-based approach can be valuable if you're working on problems where k is variable or much larger. It's always good to know multiple strategies, but remember to choose the one that best fits the problem's constraints and requirements. Great job! We covered the problem, broke it down into manageable steps, and discussed its complexity. Remember, practice makes perfect. Thanks for tuning in. Be sure to like and subscribe for more coding solutions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!